Welcome to qnawire.
For part A of the given problem, the number of allowed energy levels is proportional to the density of the states. So the ratio of the number of allowed energy at 8.50 electron volt to the number at 7.05 electron volt equals to the ratio of density of states. So we can write the ratio of states is equal to G of 8.50 electron volt divided by G of 7.05 electron volts. The density of states for an electron confined to a three-dimensional box is proportional to the square root of the energy. So G of E is proportional to E of 1/2. So we take then 8.50 divided by 7.05. We take the square root of this, and the value we get here is 1.10. So the ratio is 1.10. For part B of the problem, let me just scroll down. The number of occupied states between energy E and energy E and energy E plus dE is given by an equation that is N of E dE is equal to 8 times square root of 2 pi mass of electron 3/2 power 3/2 E 1/2 divided by H3, where H is a Planck constant, times 1 divided by exponential energy minus Fermi energy divided by KT. K is the Boltzmann constant plus 1. This times dE. Then we can let C to be 8 square root of 2 pi mass of electrons 3/2 divided by H3. Then we can rewrite the above equation using C. Then the ratio of occupied states for E1 and E2 will be ratio of occupied states will be then N E1 dE divided by N E2 dE, which is E1 divided by E2 square root and times E2 minus E F Fermi energy divided by Boltzmann constant times T plus 1, this divided by exponential E1 minus EF divided by KT plus 1, where E1 is 8.50, where E2 is 7.07 at a temperature T is equal to 300 Kelvin. We get Boltzmann constant times T to be 0.02585520 electron volts. Then the ratio of occupied states by plugging the value for E1 and E2 and KT for the equation that we wrote here, which is this one, we get the ratio of occupied states to be 9.61 times 10 to the power minus 25. For part C of the problem, comparing the results of part A and B, we see that the ratio that we get in part A is very large compared to the result in part B, which is by the order of 10 to the power 24. Therefore, we conclude that a very few states well above the Fermi energy are occupied at room temperature.